All right, welcome back to the third and final segment of our trilogy on demand-side energy management. Yeah, Star Wars has got nothing on us. I'm sure some of you are aware of this, but for those who aren't, May is National Electrical Safety Month, so it's great that we're talking about energy management. Today's topic is building and design best practices for optimized demand-side energy management, or DSM for short. We're going to look at building and design considerations for DSM, and when you're looking at those, you need to factor cost considerations, value engineering, and utility incentives into the equation. We'll talk about products and smart technologies for DSM, and we'll wrap it up by figuring out how to get DSM to work for you. Here once again to get us across the finish line of this three-part series is David Butler. He's a senior engineer who has more than 30 years of experience with control systems and electronic design. He has been published multiple times in industry publications and has presented at many trade shows. His memberships include the Illuminating Engineering Society, Association of Energy Engineers, Entertainment Services and Technology Association, and he holds his LC certification, and he's also a certified energy manager and certified measurement and verification professional. And if all that wasn't enough, he brings science back to science fiction under the pen name David Pax. Check him out at a local bookstore or library near you. By now, you probably know about PowerShift by NV Energy. But in case you don't, NV Energy wants you to know that you can never save too much energy or money. And that's why NV Energy offers PowerShift to help its residential and business customers conserve even more energy and save money on their power bills. PowerShift by NV Energy is also about providing you with excellent customer service. It's your one-stop shop to find all the energy-efficient products and services to help you boost your bottom line, along with convenient ways to manage your account. PowerShift Energy Advisors are dedicated to working side by side with business customers to discuss their needs and to find energy efficiency solutions that also save money. Plus, their Business Solutions Center is the place to go to discuss your bill payments and account-related questions. For more information, please visit nvenergy.com/PowerShift. Now, during the course of today's presentation, you can submit questions for our guests. Simply use the questions box on the right side of your screen. We're actually going to stop a couple different times during the presentation to take your questions about the topic that we've just discussed, but don't worry, because we're also going to have that Q&A that you know and love at the end of Javid's presentation. Javid, let's bring it on home.
Thanks, Mike. And just building on the Star Wars theme, having just passed Star Wars Day, May the 4th be with you. Today we're going to hopefully have Darth Vader see the benefits of green energy and convert from the dark side of the Force to using renewable resources. That might be a lot to ask for, but we'll give it a shot. Just a brief overview. In webinar 1, we discussed why demand-side management is important. Then webinar 2, we started to talk about implementing specific demand-side management strategies. And today we're going to go into advanced demand-side management topics. For those of you who are in the construction business or facility managers, we're going to start to talk about building design and operation and how that relates to demand-side management. So we're going to start with the building design considerations for demand-side management, and then touch on data mining and other analytics. Some of that may seem a little bit intimidating, but you don't have to be Google to get good value out of the data that you can already obtain from your systems. We'll talk about cost considerations, value engineering, and touch on utility incentives again, and then talk a little bit about strategic energy planning. So to start off, building considerations. There's a lot of aspects of a building that will affect your demand-side management strategies. I've listed the main ones here. For example, building orientation, shading of the building, building envelope design, the equipment selection for the building itself, and then also building operations. We're going to go into each one of these in depth. So Orientation, and you may note that I'm saying in the US because I talk about things such as southern exposure. In the southern hemisphere, it would be northern exposure. And design for buildings that are located along the equator is different as well because you don't have the same sun angles that we do here in the northern hemisphere. But building orientation can have a large impact on external heat gain. So any zone with southern exposure in the US will have more heat gain and will be more sensitive to temperature shifts. So if you have a building that is oriented with a large southern exposure where there's a lot of windows facing south, you're going to have more heat gain, and you're going to have potentially issues in the late afternoon when the sun moves to the southwest and you've already got all of the heat gain from earlier in the day, and then you start to get heat gain on the western face of the building as well. One of the buildings that was involved with an NV Energy project here in southern Nevada had an issue where we had to opt out a particular zone because it happened to be that the manager's office was on a southwest corner of the building. And so when we were implementing the demand management strategies, his office would wind up getting too warm in the afternoon. That was really more about the orientation of the building and the location of his office within the building than it was the demand management strategy itself. Overall, the DSM strategies that we were employing did save energy in the building and overall made the building operators very happy. But it happened to be that somebody who was in a senior management position was in that southwest office, and his office would just heat up a little bit more when we were trying to employ those strategies. So it's important to consider the zones that are affected, the way that external heat gain is going to impact a building, and the way that the occupants of a zone are going to react to that. There are many, many different ways that you can approach things such as furniture layout and ways that you can approach the way that people are placed. You know, if you put people right next to a window, yes, they're going to have good views, which is great, but you also then are going to have to consider what the heat gain is going to be for those desks, for those workspaces. And maybe it makes more sense to put, for example, say some low filing cabinets or shelving directly against the window, move the people slightly away from the window, 10 feet or so, and that way they still have a view out the window, but they're not getting that direct heat through the window during the late afternoon. And of course, using the daylighting that you are getting as much as possible will help with your demand side management. One of my favorites is the use of light shelves. This is a technique that is very inexpensive, and I don't see it used anywhere near as much as really would be ideal. A light shelf, very simply, is a shelf that is located, it's a structure that's located about 6 to 8 feet off the floor if you're talking a typical 10-foot ceiling, and it's painted white on the top. And what it does is it bounces the light that's coming in through the top couple feet of the window further into the space. So you have the light shelf that's painted white. You have a ceiling that is usually a fairly light color. The typical IES estimate would be 80% reflectance. So now you get the light coming into the window, it bounces off the light shelf, it bounces off the ceiling, and that daylight is now distributed through the space in a way that is using the light more effectively while not increasing the heat gain. the heat gain is still constant as far as the properties of the window itself, the solar heat gain coefficient of the glazing, whatever coatings have been applied, that's still the same. But adding a light shelf allows you to use that light more effectively. And at the same time, it provides a little bit of shading right near the window, so you don't have as much of the direct heating on the areas around the window while you're still getting the use of the light and reducing potential discomfort for people who are located near the window. Of course, by putting the light shelf at 6, 8 feet, people still get excellent views out of the window. So you're not blocking views, but you are using the light more effectively. Very simple way to implement a strategy that will reduce your energy use, your lighting energy use, and not increase your HVAC. That said, we'll talk about this more under the building envelope, but of course, if you can reduce the heat gain through the windows overall, that's even better. New construction, when you're looking at the way that the building is going to be sited, you may not have any choice, right? Depending on the piece of land that the building's located on and the normal flow that the building is going to require, you may not have any choice but to build it with a large southern exposure. But if it's possible to, say, orient the building at, say, a 45-degree angle so that you don't have a whole face of the building with direct southern exposure all of the time, then that will help. Not every building can be built with, say, a south-facing berm or a parking garage or other structure on the south side that would block sunlight while having primarily northern exposure for view windows. That's not practical in many cases, but if it is possible to orient the building so that you don't have a whole large face of the building getting that direct solar heat gain throughout majority of the day, then that will help with demand side management as well. New construction, particularly here in Southern Nevada, where we've just adopted the 2018 IECC, we have a requirement for daylight controls that now is fairly specific and requires daylight controls that are even separately zoned as you look at different orientations of the building. So another advantage of, say, orienting a building at 45 degrees to a cardinal orientation is that you would only have 2 daylight zones, southeast and southwest, instead of 3, east, south, and west, as you're looking at your control system. So considering how the building is going to be oriented is very important when you're looking at demand side management. Shading can also be very important. There are many sites that are looking at going to a zero net energy strategy. And if those buildings are being shaded by other buildings, trees, here in Southern Nevada, mountains, they can affect your choice of integrated demand side management strategy. So you could have limitations on the use of solar, and you have to account for shading effects because, of course, lower floors are going to see more shading than upper floors, and so you may need to have different DSM strategies for each of the floors. In some countries, for example, in the United Kingdom, they even now have a right to light where people have a right to receive a certain amount of daylight on their property, and it restricts what can be built around them. And that's a developing concern globally. On the flip side, if you're trying to limit the amount of solar heat gain, you can design shade structures into the building. So you can add shading on the exterior of the building as decorative elements, and you can even add them to existing buildings in some cases where you're shading the windows from that direct solar heat gain during the peak of summer. During the winter, when you've got lower sun angles, you'll still get some nice light coming in through the windows. But during the summer, shade structures that are located either high on a building, up near the parapet, or perhaps at several heights along the height of the building can help reduce that midday sunlight that would otherwise be delivering a lot of heat directly into the building. And you can also make that solar shading dual purpose. I think most people are familiar with the famous Welcome to Las Vegas sign right on the strip. And a few years ago, there were solar canopies added to the Welcome to Las Vegas sign. The canopies essentially offset the power that the sign uses. But if you drive by during a hot day in the summer, you'll see that all of the people who are waiting to get their picture taken with the Welcome to Las Vegas sign are all gathered underneath the solar canopies to be in the shade. So looking at the dual purpose potential for combining solar with shading can be very beneficial. Then the building envelope design. Many times people think that existing buildings are just stuck, that you have what you have, and it's very expensive or difficult to do anything better, which isn't always true. For example, it is possible to use window films to reduce the solar heat gain through south-facing windows. You can use heat-rejecting coatings. There's some very interesting coating technologies available now that will reject the heat from the building, and that can be mixed into paint, applied to the outside of the building, and then you're reducing the amount of heat gain through, say, concrete if it's a tilt-up building, as well as reducing the heat gain through the windows by using window films. An example is LinkedIn just modified a building. They purchased an existing tilt-up building in Sunnyvale, California, and they went LEED Platinum with this building and combined the use of on-site solar on the roof. They added skylights, and they did extensive modification to the building, and wound up with a zero net energy building. And this is just a very conventional concrete tilt-up structure that is now zero net energy by combining solar power on the roof and improved design within the building itself. Another new technology that is very interesting for both new construction and existing buildings is vacuum insulated glass. Everybody's familiar with the principle of the thermos, where you've got a glass bottle that's holding your actual hot or cold beverage, and then there's a vacuum seal between that glass bottle and the outer container of the thermos. It's the same principle for vacuum insulated glass. The reason it took a while to get to this point is that glass itself has a little bit of flexibility to it. So when you pull a vacuum inside of a glass window pane that only has a very small gap, it pulls the glass in and you don't get any benefit. What they've done now is develop these very tiny posts. You have to look very closely to see them, but they're these very, very tiny posts that get inserted in between the panes of glass so that they're able to pull a vacuum in between the panes, and it provides a much higher insulating value even than conventional double or triple pane glass that has, say, an inert gas filler in between the panes. visible transmittance is very high. You're looking at being able to get an R12 or an R14 value out of window glass. And they also manufacture it with a little port so that if for some reason the seal is ever lost on the glass, you can reseal it and then repull the vacuum so that you can maintain the insulating value for a long period of time. Another strategy with building envelope design is to create gaps using, for example, architectural mesh or plants between the surface of the building, the outer surface of the building, and the actual building envelope. If you can keep heat gain from reaching that building envelope, you can significantly reduce the amount of external heat gain on the building and thereby reduce the cooling energy required. I'm going to show you an example of that in a few slides. Equipment efficiency. We've talked some about this in previous webinars, but HVAC equipment uses 30% or more of the building energy. If you are upgrading equipment, if you need to replace it, if it's at end of life, replacing it with new efficient equipment will save you considerable energy, and you probably will also be able to get utility incentives to help with the cost of replacing that equipment. Lighting is another big one. LED lighting is considerably more efficient than old T12 lights. Now, some areas of the country have already done a pretty good job of upgrading from T12s to more efficient T8 or T5 lighting. But if you're in a part of the country that has older T12 lamps, or if your facility still has older T12 lamps, upgrading to LED can significantly reduce your lighting energy cost. And again, you can probably get some utility incentives to help with that upgrade. Process equipment. This is an interesting one because many times there are assumptions about process equipment that aren't necessarily valid. You need to think about how the equipment is being used. Last year, we did a project with NV Energy where a printing company had a large shredder. And when I say large, think of your typical office shredder blown up to the size of a house. That shredder was essentially left running so that whenever there was waste, it could be just dumped into the shredder. Well, as part of this program, what we did was we automated the startup and shutdown of the shredder. A lot of the reason that they left it running was they didn't have an easy way to turn the whole thing on and off. And by adding just a little bit of control automation, we were able to make it easy for them to turn the shredder on and off, and then they could shut it off during peak hours when the energy was very expensive. As part of this, they purchased a few storage bins, and so when the shredder was shut off, they simply would accumulate the material until they were outside of peak hours, and then they could turn the shredder back on and process whatever material had accumulated in that time. Previous to that, the shredder was left on 24/7, and that had considerable energy cost savings because they now were able to shut this down during the peak hours when energy costs were really spiking. That's in this case, that was between 1 and 7 p.m. So sometimes it's just a matter of adding some automation, and you just need to look at the systems and understand how they're being used to understand how you might be able to save some energy. Plug loads. As more and more computers and other electronics are being deployed in the office environment, we see that plug loads are replacing loads such as lighting as higher energy consumers. At a point in time when, say back in the 1950s, when most of the work was being done with manual typewriters, plug loads were not a huge energy consumer in the office environment, but lighting was, because some of the lighting at that time was even incandescent or early fluorescent. It was not very efficient. And so most of the building energy was being used in lighting and HVAC. As we've transitioned to more and more computers and electronics, and as lighting has been getting more and more efficient, the lighting portion of the building load is coming down, but the plug load portion is increasing. And to address that, there are devices such as smart power strips. For example, you can buy a power strip that has a small desk-mounted occupancy sensor, and then when somebody's away from their desk, it can do things such as shut off task lights and perhaps even monitors other loads that are not sensitive. But the plug strips also come with some unswitched outlets. So you can have, say, the computer plugged into an unswitched outlet, so it's not being turned on and off, but the other ancillary loads that are typical of today's office environment can be switched off when somebody's away from their desk. There's several different types of power strips. There's ones that have occupancy sensors. There's also other strips that have a primary load that detects the amount of load that is on that particular receptacle, and when that load is turned off, it turns off the rest of the power strip automatically. So that way, for example, if you do plug the computer into that primary port, when you shut the computer down, it will automatically turn off power to, say, the monitor and task lights and other loads around, which could also include small phantom loads such as USB chargers or radios, other small devices that don't necessarily take a lot of power, but over time consume a lot of energy. And then occupant education about energy use can also be a very effective way of helping to manage plug loads. Many times the convenience of our modern technology leads people to ignore or at least not consider deeply the amount of energy that these devices are consuming. And simply educating people about the amount of energy that's being consumed can be very helpful. That's been proven in some cases to really reduce overall plug load demand. So this is just an example that we had looked at before regarding demand management and the way that scheduling, in this case, can help save energy. This is from a previous webinar where you can see the overnight setback, and then the cooling load doesn't really start to kick in until just before the building opens up. And then once people start to show up, the cooling set point shifts to the comfortable set point for people to work. But this is a good example of ways to manage energy within a building and reduce the overall consumption. Then building operations. We have covered some of these before, but I'll just briefly touch on them again. Scheduling the building systems to run only when needed. For example, staging the cooling startup. In the first webinar, I showed the example of a large peak demand that occurs first thing in the morning if the chillers start up, say, or the rooftop units start up at 4 or 5 in the morning, long before anybody's showing up for work. By staging that and having some of the units start to cycle earlier in the day, but not having all of them come on at once, can save considerable energy and also reduce peak demand charges. Then also using networked lighting controls. One of the advantages with a networked lighting control is that you can change the operating parameters of the individual devices over the network. So for example, during the day, occupancy sensors might be set to a 10-minute timeout, but outside of normal work hours, the network could then change those occupancy sensors to operate with a walkthrough mode, where they might not even turn on lights if they don't detect people there for a few moments. The walkthrough mode is great for open offices, for example, where if nobody's there and somebody's just walking through to get to another part of the building, it will only control the amount of lighting required for them to safely walk through and not turn on the whole open office. And then another aspect of building operations is using the data from the building systems to help manage the space better. So there's a wealth of information available from most modern building systems. HVAC systems often have trending. However, that trending is typically only set up for diagnostic purposes. So it might only record 18 to 24 hours of data, and then it'll start to overwrite it. And that's useful for a facility manager to troubleshoot, but it doesn't really help you manage. So setting the trending to record indefinitely can really help you get the amount of data that you need to start to develop some management strategies for your HVAC system. Lighting data, when you have networked occupancy sensors, it'll show you when and where people are working. There's one situation that I'm aware of where, and this is an unusual situation, but it was a building with networked occupancy sensors that had an active shooter condition. And through observing the location of the shooter on the lighting control system, the security people were able to get people away from the shooter and send police to the shooter. So that's an extreme example, but overall lighting data from those occupancy sensors can tell you where people are, when they're using spaces, and that can help you plan for space, because there are times where perhaps buildings are underutilized or overutilized, and by looking at that occupancy data, you can say, you know what, maybe we could consolidate a little bit here and shut down this part of the building more frequently and save some energy there. Or perhaps the lighting data might say, you know what, we're running over capacity most of the time. We need to add some space. And that data will help you make those decisions well. It won't just be anecdotal information, it will be actual occupancy data. And then you can get 15-minute interval data from your utility that will show your whole building consumption. And that essentially shows every 15 minutes the amount of energy that the building used in the previous interval. So you can take all of that data and merge it into one database for analysis. By plotting different parameters against the 15-minute interval data from the utility, you can see how your settings are affecting your overall energy consumption and demand. Now, understand that there will be some data cleanup, and I'll illustrate that in the next slide, but understand how the data is being cleaned, because if you do it using good data cleaning methods, then you'll have reliable source data. And this isn't something that necessarily requires a lot of complicated software. We do a lot of energy analysis just using standard spreadsheets. Spreadsheets typically come with chart tools to help you provide visualizations, and there's also standard analytic tools that are available. So if you look at these two little snapshots here, you'll see that under add-ins, this happens to come from Excel, but there's other tools, other spreadsheets available that have similar tools. So under add-ins, you simply enable the analysis tool pack, and then once the analysis tool pack is enabled, you can go and under the data analysis button, open up this additional data analysis window that will allow you to run various statistical analyses of a data set. So it's really not complicated to use some fairly powerful tools to take a look at the data that you have from different sources, analyze it, and then start to plan your energy management strategy, understand where you're going to get the most value from your operations. This is just a data cleanup example, and a couple of different ways that you can clean up, for example, missing data. For example, you can see at the 5 a.m. Interval, that was filled in just using an average of base load values. So the base load is typically going to be fairly consistent day to day. It might have some variation, you can see here. And this data is just illustrative. It's not data from an actual building. But there'll be some amount of normal variation in the base load as different systems cycle on and off. Water heaters kicking in to maintain temperature, cooling systems operating for a short period to maintain temperatures as well. So during those hours where you have a fairly stable base load, you could just take the average and fill in that value. You probably will not be adding a lot of error to your calculations by doing that. Now, during the morning ramp up, the values are changing very rapidly. So in that case, you would want to interpolate just in the ramp. And in this case, the value of 200 was filled in using the ramp up values starting at about 6 a.m. and going to 10 a.m. And that way, again, by matching the slope of that ramp up through that period, you're probably not going to experience too much of an introduction of error. Now, there are some times where you have multiple data points that are missing or are inaccurate for some reason. And so at 4 and 5 p.m., I illustrated using intervals that were filled in using recent day data. For example, if outdoor air temperatures were 110 degrees on the day with the missing data, you can look back a couple of days and say, oh, last Tuesday, temperatures were also 110, and take the data from those days and use it to fill in. And again, it'll probably not introduce too much error if you're using these techniques. What I'm really trying to illustrate here is that many times there is data available to do some very good analysis, and the tools are also available and easy to use to help you understand more about how energy is being used in your building. Again, we use spreadsheets extensively to do analysis and find it very effective. Now, there are some more advanced tools available. If you either don't want to use a spreadsheet or feel that you need more detail than what the spreadsheet might give you. So one of the tools that we use is Energy Toolbase, and that helps us model buildings for solar plus storage. For residential buildings, there's Energy Pro and also NREL BIOP, which is free. There's many other tools available to do energy modeling. I'm not trying to list them all here. I'm just giving some examples of tools that we have used to do some energy modeling above and beyond spreadsheets. So let's put all of this together. This is a building that is in Harare, Zimbabwe. And what they did was they used the design of termite mounds to design the building. So they looked at the way that termites manage temperatures within termite mounds, and they used that in the design of the building. As a consequence, this building uses only 10% of the cooling energy compared to other similar buildings in the area. So that is a significant energy savings. And this goes back to what we were talking about earlier with things such as the siting of the building, the design of the building envelope, the design of the systems. So this used vegetation on the outside of the building to reduce the amount of sunlight that was actually striking the building envelope, and thereby reducing the heat gain through the building envelope while still providing for attractive views. Then the termite mound strategy uses fans to bring cool air in, and there's a lot of thermal mass in the core. So the cool air comes in low, it's then distributed low through all of the spaces. It picks up heat in each of the individual spaces, and then is funneled into a heat exhaust that goes up through the core of the building using natural ventilation. So the chimneys essentially pull the hot air up and out. The fans bring fresh, cool air in, and as a consequence, they don't really require extensive mechanical systems to maintain comfortable temperatures within the building. As I mentioned, it uses about 10% of the energy that a comparable building does. So these are the kind of strategies that can be employed. And these are strategies that work very, very well. Termites have been building mounds using this type of cooling strategy for about 21 million years. I would call that a proven technology. So let's talk about costs a little bit. Many demand-side management projects in existing buildings have less than a 3-year simple payback. So the upfront cost is not really the consideration that is important. When you have a 3-year simple payback, it really is not taking very long before that demand-side management measure is starting to pay itself off and return savings to the building. Also, many LEED buildings, for example, have the same first cost as comparable buildings, but a significantly reduced operating cost. So, for example, LEED certified, LEED silver buildings can actually cost even a little bit less to build than a comparable building, because the documentation process required for LEED means that the building is really very, very well designed from the beginning, and it reduces costs during the construction process. Now, to be fair, if you're going for LEED Gold or LEED Platinum, you're looking at small increases, maybe 5 to 7% more than a comparable building. But when you're operating at a level of LEED Gold or Platinum, then you have productivity gains as well as energy savings. So, for example, the LinkedIn building in Sunnyvale is LEED Platinum. That's a building where they have a lot of their design engineers. They really want those engineers to be working at optimal productivity. So they designed a space that was very conducive to really having those teams work at peak efficiency. But we've also seen LEED Platinum for retail. Nike has a LEED Platinum store here in the Las Vegas Valley. There's also Las Vegas Cyclery, which is a LEED Platinum bike shop. And when you're getting to that level with LEED Gold and LEED Platinum, many times you do get those additional benefits. It makes a retail environment more comfortable, more inviting for people to come in and stay, and if it's a retail environment, to purchase a little bit more. So it does pay for itself in the long run. tech companies, design offices, those are some other examples where the additional productivity benefits will often exceed any of the construction cost increase. And then just as a reminder, utility programs can help to pay for these demand-side management measures. NV Energies is simply nvenergy.com, save with PowerShift, and you'll get a screen that looks like this. And from there, you can either click on residential or on commercial programs to start the application process to get a utility incentive to help with the measure that you're looking at. Those incentives are available to help reduce the cost of demand-side management in both existing buildings and new construction. It's different programs typically. So if you're looking at building a new building or adding to an existing building, be sure to talk with the folks at the program about what you're trying to accomplish and what incentives are available to help with that. Now, when you're building a new building, it's not uncommon for contractors to come back with a value engineering proposal. It's a proposal that reduces the first cost, but with the newer technologies that are involved in demand-side management, that will often increase the operating cost of a building. For example, it might cost less upfront to use a higher SEER rating on your RTUs, but that is going to have a much higher operating cost over the life of the building. So if you do get a value engineering proposal, it's important to look at that and consider what that lifetime, that life cycle cost is really going to be. Because more efficient HVAC equipment is becoming less and less expensive all of the time, and the benefit of saving a little bit upfront versus the operating cost over the life of the building could be significant. Also, if you are in an area that uses the IECC, such as Nevada, your compliance with Section 406 could be affected. For example, if the design team chose, if you as the building owner or operator and the design team chose to use the advanced lighting controls path to comply with Section 406, and the electrical contractor comes back with a VE proposal that removes the advanced lighting controls, you might not pass inspection for the energy code if that if the lighting controls aren't installed the way that they were originally designed. So you need to be aware of that and make sure to communicate that to the contractors. Also, if, for example, you had specified advanced lighting controls, fully networked, individually dimmable fixtures, which are very common now, very easy to obtain, going to a lower first cost package will likely result in higher operating costs as well, because you'll be using more energy than you would if you had the advanced lighting controls installed. So strategic energy planning helps you control costs and avoid expensive surprises. This is where you can use the data from your existing systems to examine equipment, see when equipment might be starting to reach its end of life, plan for an upgrade, and make sure that you are operating as efficiently as possible. You want to start this by understanding your rate plans. We talked about rate plans in webinar 1. Also check utility websites for new programs. If you're a large customer, get to know your major account executive and ask them to keep you updated on new programs and pilot opportunities that can help you save energy. These are all just very simple things that you can do as part of a strategic energy plan. From there, you can then implement the demand-side management strategies that we discussed in webinar 2. HVAC upgrades, improved scheduling, staging of HVAC startup in the morning, lighting upgrades, process equipment upgrades, and management. Also, have a strategic plan for replacing older equipment. Many times, older equipment, whether it's cooling equipment or process equipment, is less efficient, and there are newer types of equipment available that can help you save energy. Now, those are often high capital costs. So having that strategic plan to understand when you're going to need to replace those can help you manage your capital budgets and improve your energy efficiency without it being a strain on the capital for the company. If you're using incentive programs, they can have yearly caps. So this is also a good reason to talk with folks such as the folks at PowerShift and plan out your energy projects, because the caps will cap how much of an incentive you can receive in a year. It will typically start to reduce the incentive payments as you get closer and closer to the cap. So having that strategic energy plan, understanding when you're looking at replacing equipment and what incentives are going to be available to help defray those costs is very important. And then, as we discussed, plan new buildings to be as energy efficient as possible. I'm not saying that everybody's going to be able to build a building such as the Eastgate Center with the termite mound cooling system, but you can look at some of those strategies, as well as more basic strategies such as the building orientation and the envelope considerations, and make them as energy efficient as possible. So, conclusions. The building design can have a significant impact on demand-side management, and it's important to consider the building design as you're looking at your overall energy plan. Analytics are relatively easy to do, at least on a basic level, and they can really help you understand more about your energy consumption and improve your project performance. Costs can be offset very often by utility incentives. Look at value engineering very carefully. It's not the way that it was 10 years ago, when it didn't necessarily matter as much if you got a less expensive fluorescent troffer and perhaps saved a little bit of money doing that. Now, as we have much more sophisticated controls and more efficient equipment, it's very important to look closely at any value engineering proposal and make sure that it isn't going to cost you more in the long run. And then developing your strategic energy plan helps you avoid unexpected costs and helps you make the best use of incentives. So with that, Mike, we have time for some questions.
That's right, sir. I appreciate it very much. And to our audience, please don't forget to send in your questions using that questions box over there on the side. You know, I had one. You had a slide about shading, and you talked about using trees as one method for using shading.
Mm-hmm.
Do you ever run into a situation or factor this into any calculations of using trees for wind blocks? I've seen this strategy used in rural areas and on farms, especially when I go drive to visit my in-laws in north central Iowa. You'll see this row of evergreens, and it's meant to help block the wind, usually from the north, that might, you know, batter the house in the winter. Can you talk a little bit about if that even comes into consideration at all?
So I haven't really seen any sort of wind screening used, but there's a very interesting concept that you could use microturbines, you know, an array of microturbines, or any sort of wind power generation system to provide wind screening for buildings. I've got relatives in central Wisconsin, so I'm very familiar with the rows of evergreens that you're talking about that separate fields. As a matter of fact, it is a common topic of discussion amongst my family that lives in that area, the way that some of the larger commercial farms have removed the windscreens, and now all of a sudden they're losing their topsoil because the wind just screams across the open area and blows away all of the topsoil. In principle, you could do, as I said, an array of microturbines that would serve that wind screening purpose, but I haven't seen that done, probably because when you get into urban environments, the wind is more of a nuisance than a real problem. But there are some places, here in southern Nevada, we get some very high winds at times because we live down in a valley, and the temperature differences between day and night create some very strong winds at certain times of the year. And in principle, people could be hit by flying objects, or there might be other potential safety reasons why you might want to slow down the wind or diffuse it a little bit. And you could use trees for that, or could use wind generators.
And I recognize too, I'm talking about a residential setting rather than commercial or industrial. So, wanted to make sure I noted that in this discussion as well. Hey, we do have a question from Ravi. He wanted to know if there's any particular window film type that you recommend, because there's just a lot of specs out there.
There are a lot of specs. I'm trying to remain product agnostic in these presentations, but you do want to look at all of the specs, such as the visible transmittance. Typically, for example, a better quality window film will have a reasonably good visible transmittance, which is often abbreviated VT, as well as reducing the solar heat gain. So look at those kind of specs. A lot of times they are hidden on the packaging because the manufacturers, of course, would just like you to buy the nice, pretty box of window film. But a good quality window film will have a good visible transmittance as well as reducing the solar heat gain.
Gotcha. Great. Well, I don't see any other questions, David, so I wanted to thank you so much for spending all your time with us over these past 3 webinars and really taking a deep dive into DSM. We really do appreciate it.
Well, you're very welcome. And if people have additional questions, my contact information is on the screen. They can feel free to email me.
Please do. If you see that on there and you need to answer more questions, please reach out to him. That concludes this series on demand-side energy management, but we've got more webinars on tap for you. We're going to hold another webinar on June 26th with Matt Power, and in that one, we're going to be looking at building science best practices, and that's going to start at our usual time of 2 p.m. Eastern. And stay tuned to your inbox, because we might get another webinar scheduled sometime prior to the June 26th date, so stay tuned there. Until then, I hope everyone has a great week, and if you get a quiet moment, please send some positive thoughts to those who are affected by the flooding in the Midwest. They've got quite a mess in their hands right now, and they're going to continue to have that mess for many weeks ahead. So I know they'd appreciate anything and everything that you can offer. Take care, everyone. Goodbye.